Welcome to the lecture on damped free vibration. So, in the previous lecture, we discussed the free vibration of a single degree of freedom system having mass and stiffness. There was not a damping element, so there was not a dissipation of energy in the system. So, the vibration of the system was maintained forever. There was no reduction in the amplitude of the vibration. Now, if we introduce a damping element in the system, means we have M, we have K, now we have the C, the damping element in the system, then what will happen? Like in the case of the free undamped vibration, we had the vibration of the system with the natural frequency omega n. Now, will the damped system will vibrate with the same frequency as omega n or different? Will the amplitude of the vibration remain constant or it will change with the time? Will it decay with the time? Will it increase with the time? So, all these questions that we will discuss in this lecture. So, before we will discuss type of damping, because when we want to discuss the damped free vibrations, there are several types of damping. The most common is the viscous damping, because this is very important and simple. So, it is used vastly. Then we have the dry friction or Coulomb damping, then solid or structural damping, then slip or interfacial damping. So, here viscous damping occurs when a piston in certain fluid that has some viscosity, the piston moves in the fluid and the fluid is allowed to pass through some orifice. So, there is the small velocity of the movement of the piston. So, this kind of damping, we can see that the force and velocity relationship, that is really linear. Here is the force F equal to C into V, where F is the damper force, C is the damping constant and V is the relative velocity. Here we can see one damper, and if some force is applied, here is the piston, and it is moving, and here is the orifice through which the fluid is passing. So, this kind of damper is called the viscous damper, because they are based on the principle of viscous damping. Why we give this so important to this kind of damping? Because here the force viscous this damping force is directly proportional to the velocity, so x dot. So, if we use this, put this force in the equations, differential equation of motion of the system, that makes the equations differential equation linear. So, that is why we this damping is more important. Several times we use the equivalent of the other type of damping, equivalent viscous damping for the other type of damping, just for this reason. We represent this damping C like this symbol. Then another type of damping is friction, dry friction damping or Coulomb damping. So, whenever a mass is sliding on some surface, there is friction between the two surfaces, and due to the friction there is some energy dissipation, because the basic role of the damping is the energy dissipation. So, like in the viscous damping, it was the energy dissipation due to the in the fluid, and energy dissipation is usually results into heat and sound. So, here when a mass is sliding on a surface, due to the friction there is energy dissipation into heat. So, when there is dry friction, here the damping resistance is constant because it depends on mu, and therefore it is independent of the rubbing velocity. So, here we can see we have a mass that may slide on the surface, and due to the friction between the two surfaces there could be the energy dissipation, and this kind of mechanism is called Coulomb damping. Now, we have another type of damping, that is called solid or structural damping. It is also called material damping or hysteresis damping. So, there is various name to this damping. So, we can see the stress strain diagram, and stress strain diagram when there is a material that has this kind of damping, the stress strain diagram may form a hysteresis loop. This loop, that is the area, there is some area between stress and strain, and the area shows the energy dissipated in one cycle of this loop. So, this energy shows the energy that is due to the friction in the molecules. So, there are the molecular deformation in the material. So, therefore, this damping depends on material, the frequency and amount of the dynamic stress. There is one more type of damping, that is interfacial damping or slip damping. So, we have several mechanical parts, and there is roughness between these parts, and when they come into contact they meet. There is some micro level of interfaces and rubbing, and that is that makes the energy loss, energy dissipation. For example, there is some joints like bolted joints and some machine parts. So, this damping depends on the roughness of the surfaces, the contact pressure and the amplitude of the vibration. Now, in this lecture we will discuss we will take the viscous damping. As we said that taking the viscous damping, there is certain advantage that it makes the differential equation linear, and so it is easier to solve these kind of equations. Therefore, we start with a single degree of freedom system having viscous damping. So, we can see here we have a spring, damper and mass system, and again it is a free vibration case. So, due to the free vibration we will have due to the free vibration we will give some initial disturbance to the system, and then we will isolate this mass to make a free body diagram. Means we have to show the forces that is acting on the body, and then we have to apply the Newton's law of motion to write the differential equation. So, let us do it. So, we take the single degree of freedom system. So, this is the system having the spring, damper, and this is mass. So, we disturb this system. So, we put here x. Now, we make a free body diagram. So, this is the mass m, and because we have pulled this system x and it has the velocity x dot, so we can make the show the forces. So let's assume this is the direction of x double dot, and because we have pulled this system with x, we have a spring force kx, and this is x dot, so we will have here cx dot, because when we pull it, the damper or spring will apply force opposite to this pull. So this is our system. Now we have to write the equations. So here we have sigma f equal to mx double dot. So sigma f, we have two forces, spring force and damping force. So here it is minus kx, because their direction is opposite to the direction of x double dot, that is why we are giving negative. So minus kx and minus cx dot equal to mx double dot. So we can write mx double dot plus cx dot plus kx equal to 0. So this is the equation of motion of free vibration of this system. Now if you see, if we put c equal to 0, means if we remove the damping, our equation results mx double dot plus kx equal to 0. So it is the same as undamped free vibration case. Now we have to solve this equation, and to solve this kind of differential equation, we assume a solution x equal to e power st. So we have assumed one solution, x equal to e power st, and we put this into this equation 1. So put this x equal to e power st. So x dot equal to s into e power st, and x double dot equal to s square into e power st. So we put these values in this equation. So m into s square e power st plus c into s e power st plus k e power st equal to 0. So here we can take e power st outside. So e power st ms square plus cs plus k equal to 0. So because this is exponential, so this can't be 0. So e power st can't be 0, that's why this term should be 0. So ms square plus cs plus k equal to 0. Now this is a quadratic equation in S. So we can write the roots, it will have two roots. So let's write the roots. So S equal to, so it is S1 and S2 equal to, so minus b plus minus under root b square minus 4 a c upon 2a. So 2a. So minus b is c, so it is minus c, plus minus under root b square, so it is c square, minus 4 a is m, and c is k, upon 2a. So 2 and a is m. Now here we can write so minus c by 2m plus minus one by 2m under root c square minus 4 m k Now the solution of this differential equation, if we have roots, so roots, these roots S1 and S2, they can be real and distinct. So we will have solution x equal to C1 e power S1t plus C2 e power S2t. If they are equal and real, so we will have solution x equal to C1 plus C2 t e power st. So because s is S1 or S2, anyone. If they are complex roots, so we have if complex roots, so that is, let's say, alpha plus minus I beta. So this is if this kind of complex roots, we have S1 equal to alpha plus I beta, S2 equal to alpha minus I beta. So we have x equal to e power alpha this C1 cos beta plus C2 sin beta t. So these are the solutions depending on the different conditions of the roots. So roots could be either real and distinct or real and equal, or they could be a complex pair. So in these three conditions, the solution will be given by these equations. So now let's so this is our equation. Now we define certain terms. So let's say now we define critical damping. So critical damping comes when we have the equal and real roots. So equal and real roots means this term is 0. So c square minus 4mk equal to 0. So here we have, and this c is cc. So we call it cc square minus 4mk equal to 0. So cc equal to under root 4 mk equal to 2 root km, or we can write it 2 into m into omega n, because omega n is root k by m and m will cancel out. So the critical damping is the damping that we obtain when our roots are equal and real. It means this part is 0. So this in under root part is 0. So we get cc equal to 2 root km or 2 m omega n. Another thing we define, that is damping factor. So damping factor zeta equal to c by cc. So c is the actual damping value and cc is the critical damping value. So the ratio of this is c by cc. Now we write this equation of s in this term. So s equal to, so first we write c by m. So c by m equal to c by cc into cc by m. So zeta into cc by m is 2 omega n. So equal to 2 zeta omega n. Now we write here we can write here minus c by 2m plus minus one by 2 root c by m whole square minus 4 k by m. because here m will be m square when it will go inside. So 4 k by m. K by m is 4k by m, and k by m equal to nothing but omega n square, because omega n is root k by m. So now we can write these values in this equation. So s equal to minus, so c by m is 2 zeta omega n, and it is by 2, so it is minus zeta omega n plus minus 1 by 2 under root c by m square. So c by m square is 2 zeta omega n square minus 4 into omega n square. So here we will get minus zeta omega n plus minus 1 by 2, and this is 4 and this is 4, so 2 will come out and it will cancel out, and omega n square omega n will cancel out, so this will be cancelled out, omega n root zeta square minus 1. So here we can write equal to minus zeta plus minus under root zeta square minus 1 omega n. So these are our roots. So our S1 equal to minus zeta plus root zeta square minus 1 omega n, and S2 equal to minus zeta minus root zeta square minus 1. Okay. So these are the two roots S1 and S2 that we have obtained. Now depending on conditions, we have to fit these in these three conditions. We have to see in which condition these roots are coming. Okay, so now I remove this part. So now here if we have zeta equal to zeta is equal to 1. So if we have zeta equal to 1, so this is 0, this is 0, we will have S1 equal to S2 equal to minus zeta. So it means we have equal and real roots. So we will have x equal to c1 plus c2 t e power s is minus zeta into t. Okay, for zeta equal to 1. Now if zeta is greater than 1, so zeta is greater than 1, we have S1 equal to minus zeta plus root zeta square minus 1 omega n, and S2 equal to minus zeta minus root zeta square minus 1 omega n. So here we see that because zeta is greater than 1, so this quantity is greater than 0, this is greater than 0. So these S1 and S2 are real and distinct. So we will have this equation. So we will have x equal to C1 e power S1t. So S1 is minus zeta plus root zeta square minus 1 t plus C2 e power minus zeta minus root zeta square minus 1 t. So it is minus zeta into omega n. So here it will be into omega n. Here into omega n, and here is also into omega n. So we have minus zeta plus root zeta square minus 1 omega n into t plus C2 e power minus zeta minus root zeta square minus 1 omega n into t. So here we have the condition when zeta is greater than 1. Now the another case we will have. So let's have the other case. So when zeta is less than 1, so we take a case when zeta is less than 1. So when zeta is less than 1, we will have S1 equal to minus zeta plus I root 1 minus zeta square, because we can write here is minus 1 minus zeta square. So minus root minus can be I into omega n, and S2 equal to minus zeta minus I root 1 minus zeta square omega n. Now here we see that we are getting a complex pair root. So here if we compare from this alpha plus I beta, we have alpha equal to minus zeta omega n and beta equal to root 1 minus zeta square omega n. So we can write the solution x equal to e power minus zeta omega n t C1 cos root 1 minus zeta square omega n t plus C2 sin root 1 minus zeta square omega n into t. Okay. So here we have reached to three conditions of based on the damping factor zeta. So zeta equal to 1. So zeta equal to 1, we get equal and real roots, and the solution means the response of the system, that is x equal to C1 plus C2t into e power minus zeta omega n t. When zeta is greater than 1, we have got the two real and distinct roots, and the response of the system x equal to C1 e power omega n minus zeta plus root zeta square minus 1 t plus C2 e minus zeta minus root zeta square minus 1 omega n t. However, for the case when the damping factor zeta is less than 1, we got the complex pair roots, and for complex pair roots we have minus zeta plus minus I root 1 minus zeta square omega n, and we have alpha, beta, and we write x equal to e minus zeta omega n t and c1 cos root 1 minus zeta square omega n t plus c2 sin root 1 minus zeta square omega n t. So these three conditions lead to us the three different type of damped systems. So these three different type of damped system, like zeta equal to 1, that is called critical damping or critically damped system. If zeta is greater than 1, we call it overdamped system or overdamping of the system. When zeta is less than 1, we call it underdamped system or underdamping of the system. So we see that in these three different conditions of damping, that is critical damping, overdamping and underdamping, the response of the system is different. So because from the expressions of the response x, we can see that their response is governed by different equations, and therefore we have if we want to study a system, we have to decide that what the damping value we want. I mean, we want our system to keep in the underdamped region, overdamped region or critical damp region, because all these different region has their own characteristics, and that we will discuss in detail one by one in the next lectures. So thank you for your attention, and see you in the next lectures. Thank you.